There's a boundary out there, a limit to everything we can see, everything we can know, everything we can ever hope to interact with. It's called the edge of the observable universe, and it might be the strangest concept in all of cosmology. This edge isn't like any boundary you've ever encountered. It's not a wall, it's not a barrier. You can't touch it or see it or ever reach it. And yet it's absolutely real, defining the ultimate limit of human knowledge. Beyond this edge lies more universe, probably much more, possibly infinitely more, galaxies and stars and perhaps even other civilizations, forever beyond our reach. Not because they're too far to travel to, though they are, but because the light from those distant places hasn't had time to reach us since the universe began. Before we dive in, if you enjoy journeys to the frontiers of human knowledge, consider giving a quick like and subscribe. Your support helps bring these explorations to life, and truly means the world to me. Now get yourself nice and comfortable. Let's begin. Let's start with something fundamental. Something that shapes everything we're about to discuss. Something so deeply woven into the fabric of reality that without it, the edge of the observable universe wouldn't exist at all. The speed of light. You've probably heard that light is fast, and it is fast. Incredibly fast. Light travels at about 300,000 kilometers per second. That's roughly 186,000 miles per second. To put that in perspective, at that speed, light could circle the entire Earth about 7.5 times in a single second. In the time it takes you to blink, light has traveled around the entire planet multiple times. In the time it takes you to snap your fingers, light could travel from New York to Los Angeles and back about 37 times. This speed is so fast that in everyday life, light appears to travel instantaneously. When you flip a light switch, the room illuminates immediately. There's no perceptible delay between flipping the switch and the light reaching your eyes. But that light did travel. It moved from the bulb to your eye, crossing maybe 5 or 10 meters of space. It just travels so fast, in about 30 billionths of a second, that your brain couldn't possibly notice the delay. As far as your perception is concerned, the light appeared instantly. The fastest thing most people ever experience is an airplane. A commercial jet flies at about 900 kilometers per hour. That's about 0.25 kilometers per second. Light travels more than 1 million times faster than that. The fastest car ever built, the Thrust SSC, reached about 1,200 kilometers per hour. Light is about 900,000 times faster. Even a bullet from a high-powered rifle, traveling at maybe 1 kilometer per second, is 300,000 times slower than light. But here's what makes light truly special. It's not just fast, it's the fastest thing in the universe. Nothing can travel faster than light. Not rockets, not radio waves, not X-rays, not gamma rays, not anything carrying information or energy or matter. The speed of light isn't just a speed. It's a fundamental cosmic speed limit, built into the very fabric of reality itself. This isn't a technological limitation. It's not like saying we can't travel faster than sound, which was true before jets were invented, but is obviously not true anymore. The speed of light isn't a barrier we might break with better technology or more powerful engines. It's a fundamental law of physics, as fundamental as gravity itself, as fundamental as the conservation of energy. It's built into the structure of space-time. To understand why this matters for the edge of the observable universe, we need to understand why this speed limit exists. We need to understand what makes the speed of light so special. And for that, we need to talk about Albert Einstein. In 1905, Einstein published his theory of special relativity. He was 26 years old, working as a patent clerk in Bern, Switzerland. He had no academic position, no laboratory, no research team. He was examining patent applications during the day and doing physics in his spare time. And in that one remarkable year, he revolutionized physics forever. Einstein realized something profound, something that seemed to contradict common sense but turned out to be true nonetheless. The speed of light is the same for everyone, regardless of how fast you're moving. This sounds simple, almost obvious, but its implications are staggering. Think about this carefully. You're on a train moving at 50 kilometers per hour. You throw a ball forward at 20 kilometers per hour, relative to you. Someone standing on the platform watching you go by would see that ball moving at 70 kilometers per hour. 50 plus 20 equals 70. The speeds add together. This makes intuitive sense. Matches our everyday experience. It's how we expect the world to work. But light doesn't work this way. Light refuses to follow these simple rules. If you're on a spacecraft moving at half of the speed of light, which is about 150,000 kilometers per second, and you turn on a flashlight and shine it forward, you might expect someone watching from outside to see that light moving at 1.5 times the normal speed of light. Your speed plus the light's speed. 150,000 plus 300,000 equals 450,000 kilometers per second. That's what our intuition says should happen. But that's not what happens. Not even close. The person watching from outside sees that light moving at exactly 300,000 kilometers per second. Exactly the speed of light. The same speed you see it moving at from inside the spacecraft. No matter how fast you're going, no matter which direction, light always moves at the same speed, relative to you. This seems impossible. It seems to violate basic mathematics. How can both observers see the light traveling at the same speed when one of them is already moving at half the speed of light? If I'm running toward you at 10 kilometers per hour and I throw a ball at you at 20 kilometers per hour, you see the ball approaching at 30 kilometers per hour. That's just addition. So how can light refuse to add? The answer is that something else has to change. If the speed of light is constant, truly constant, the same for all observers regardless of their motion, then something else in our equations must be flexible. Something we thought was fixed must actually vary, and what changes is space and time themselves. Einstein showed that space and time are not the absolute, unchanging backdrop we always assumed. They're dynamic, they're flexible, they depend on your motion. When you move very fast, time literally slows down for you compared to someone standing still. This isn't science fiction. It isn't a metaphor. It's measured fact. We've tested it with atomic clocks on airplanes. Clocks that flew around the world on jets came back running slightly slow compared to identical clocks that stayed on the ground. The difference was tiny, just a few nanoseconds, but it was exactly what Einstein's equations predicted. We've observed the same effect with particles in accelerators. Moons, which are particles similar to electrons but heavier, decay very quickly when they're standing still. But when they're moving at close to the speed of light, they last much longer from our perspective. Their internal clocks are running slow. Time dilation is real. At the same time, distances in the direction you're moving actually shrink. This is called length contraction. If you're traveling at 90% of the speed of light, distances in front of you would appear compressed to about half their normal length. A journey of 100 light years would look like a journey of about 44 light years from your perspective. The faster you go, the more space contracts in the direction of your motion. These effects, time dilation and length contraction, work together to keep the speed of light constant for all observers. When you're moving very fast, your clocks run slow and your rulers are short. These changes conspire to make light always appear to travel at exactly 300,000 kilometers per second, no matter how fast you're going or in which direction. These effects seem strange because we never experience them in daily life. We move far too slowly. Even the fastest rocket ever built travels at only a tiny fraction of the speed of light. At everyday speeds, time dilation and length contraction are so small, they're unmeasurable. But for particles and accelerators, for cosmic rays streaming through the atmosphere, for anything moving at a significant fraction of light speed, these effects become dramatic and essential. Here's another consequence of special relativity that matters enormously. As an object with mass moves faster, it becomes harder and harder to accelerate further. Its inertia increases. The closer it gets to the speed of light, the more energy you need to push it a little bit faster. At 90% of light speed, the energy required to accelerate is already immense. At 99%, it's even more. At 99.9%, the energy requirements become staggering. To actually reach the speed of light would require infinite energy. And infinite energy doesn't exist. The universe doesn't contain infinite energy. Therefore, nothing with mass can ever reach the speed of light, let alone exceed it. Only massless particles can travel at the speed of light. Photons, which are particles of light, have no rest mass. They don't need infinite energy because they never have to accelerate to light speed. They're born moving at light speed. From the moment they're created to the moment they're absorbed, photons travel at exactly 300,000 kilometers per second. Not faster, not slower. That's just what photons do. It's their nature. This has been confirmed by countless experiments over the past century. Special relativity is one of the most thoroughly tested theories in all of physics. Every prediction it makes has been verified. Every experiment has confirmed its equations. The speed of light is truly the cosmic speed limit, and nothing we know of can break it. What does all this have to do with the edge of the observable universe? Everything. Because the speed of light is finite, and because nothing can travel faster than light, information takes time to travel across space. When you look at something far away, you're not seeing it as it is right now. You're seeing it as it was when the light left it. You're looking into the past. This is true even for nearby objects, though the effect is too small to notice. When you look at someone across the room, maybe 5 meters away, you're seeing them as they were about 17 billionths of a second ago. The light needed that time to travel from them to your eyes. Of course, you can't perceive such a tiny delay. As far as your brain is concerned, you're seeing the present, but technically you're not. You're seeing the past. Everything you see is the past. When you look at the moon, you're seeing it as it was about 1 1/3 seconds ago. That's how long light takes to travel the roughly 384,000 kilometers between Earth and the moon. If something dramatic happened on the moon right now, you wouldn't see it for over a second. This became critically important during the Apollo missions. When astronauts walked on the moon and talked to mission control in Houston, there was always a delay of about 1.3 seconds each way. Every word they spoke took that long to reach Earth. Every response from Houston took the same time to reach the moon. The round trip delay was nearly 3 seconds. You can hear this delay in the recordings of the missions. There's always this pause, this lag between when an astronaut finishes speaking and when they receive a response. It's not that mission control was slow to answer. They responded immediately. But the radio signals, traveling at the speed of light, needed over 2 seconds for the round trip. Even at 300,000 kilometers per second, the moon is far enough away that communication takes noticeable time. When you look at the sun, you're seeing it as it was about 8 minutes and 20 seconds ago. The sun is about 150 million kilometers away, and even light needs over 8 minutes to travel that distance. We call this distance 1 astronomical unit, and it's the fundamental measuring stick for distances in our solar system. This creates an interesting situation. If the sun suddenly changed, if it flickered or dimmed or even disappeared entirely, we wouldn't know for over 8 minutes. The event would happen, but the light carrying that information would still be traveling toward us. We keep seeing the old sun, the sun as it was, completely unaware that anything had changed. For 8 minutes and 20 seconds, we'd be living in blissful ignorance while light from the changed sun raced toward us. This delay gets longer and longer as we look at more distant objects. The nearest star system to our sun is Alpha Centauri, a triple star system about 4.24 light years away. When you look toward Alpha Centauri, if you could see it clearly, you're seeing light that left those stars over 4 years ago. If something happened at Alpha Centauri today, you wouldn't know until sometime in the year 2030 or so. You're not seeing Alpha Centauri as it is, you're seeing it as it was years ago. Sirius, the brightest star in the night sky, is about 8.6 light years away. The light entering your eyes from Sirius tonight started its journey over 8 years ago. If Sirius exploded tomorrow, transforming into a supernova that would temporarily outshine the full moon, you wouldn't know for about 8.5 years. The star would already be destroyed, already gone, but you'd keep seeing the old Sirius, shining peacefully for years to come. Betelgeuse, the red supergiant that marks one of Orion's shoulders, is about 650 light years away. The light you see from Betelgeuse began its journey around 1375. Think about that. The 100 Years' War was raging in Europe. The Black Death had swept through just a generation earlier. Columbus wouldn't sail to the Americas for another century, and that light has been traveling through the emptiness of space ever since, crossing vast distances of nothingness, finally arriving at your eye tonight. Betelgeuse is actually interesting because it's a star that might explode relatively soon. It's near the end of its life, and within the next 100,000 years or so, it will likely go supernova. But here's the thing. It might have already exploded. The explosion might have happened 600 years ago, 500 years ago, 100 years ago. We wouldn't know yet. We wouldn't have any way of knowing. The light from that explosion would still be traveling toward us, covering the 650 light years between there and here. We keep seeing Betelgeuse shining red in Orion's shoulder, completely unaware that we're looking at a star that no longer exists. And this is where it gets really interesting. Because as we look at objects farther and farther away, we're looking further and further back in time. Distance in space equals distance in time. The deeper we look into space, the deeper we look into the past. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, is about 2.5 million light years away. When you see Andromeda, you're seeing it as it was 2.5 million years ago. Your ancestors hadn't yet evolved into modern humans. Homo erectus was walking the plains of Africa. The light that reaches your eyes from Andromeda began its journey before our species existed. Some galaxies we can see are billions of light years away. The light from those galaxies has been traveling for billions of years. When that light began its journey, Earth didn't exist. The sun hadn't formed. The matter that would eventually become our solar system was still scattered across space in vast clouds of gas and dust. The universe itself is about 13.8 billion years old. The Big Bang happened about 13.8 billion years ago, and the universe has been expanding and evolving ever since. So the most distant things we can possibly see are objects whose light has been traveling toward us for almost that entire time. But here's the crucial point. The point that creates the edge of the observable universe. Light from anything farther away than a certain distance simply hasn't had time to reach us yet. The universe has only existed for 13.8 billion years. Light can only travel so far in that time. Even at 300,000 kilometers per second, there's a maximum distance light can cover in 13.8 billion years. Beyond that distance, there's no way for any information to have reached us. Not light, not radio waves, not gravitational waves, not anything. This creates a boundary, not a physical wall, not a barrier you could touch or see, but a horizon, a limit, an edge to everything we can observe. Think about this carefully. The edge of the observable universe exists because of two facts. First, light travels at a finite speed. Second, the universe has a finite age. Put those two facts together and you get a maximum distance from which light could have reached us. Everything beyond that distance is invisible to us. Not because it doesn't exist, it almost certainly does, but because light hasn't had time to get here yet. This is fundamentally different from other kinds of limits in science. We can build bigger telescopes to see fainter objects. We can develop new technologies to detect things we couldn't detect before. But no technology, no matter how advanced, can see light that hasn't arrived yet. The edge of the observable universe is a limit imposed by physics itself, by the nature of light, space, and time. Let's explore this concept more deeply by looking at how astronomers and space agencies actually deal with the finite speed of light. When NASA operates rovers on Mars, they can't drive them in real time like a remote-controlled car. The communication delay is simply too long. Mars is between 3 and 22 light minutes away from Earth, depending on where both planets are in their orbits around the Sun. When Earth and Mars are on the same side of the Sun, relatively close together, the delay might be only 3 or 4 minutes. When they're on opposite sides of the Sun, the delay stretches to over 20 minutes. Send a command to a Mars rover, and you wait between 3 and 22 minutes for it to arrive. The rover does something, and then you wait another 3 to 22 minutes for confirmation to reach Earth. That's a round-trip delay that can exceed 40 minutes. If something goes wrong, if the rover gets stuck on a rock or encounters an unexpected obstacle, mission controllers can't react instantly. They have to wait for the images showing the problem to reach them. Then they have to analyze the situation, figure out a solution, write new commands, and transmit those commands to Mars. Then they wait again for the commands to arrive. By the time they know if their fix worked, an hour or more might have passed. A problem that might take seconds to solve with a remote-controlled car on Earth can take an hour or more to solve on Mars. This is why Mars rovers need sophisticated autonomous systems. They need to be able to identify hazards and avoid them without waiting for instructions from Earth. The speed of light makes real-time control impossible. When Voyager 1 reached Saturn in late 1980, it was about 1.5 billion kilometers away. Communication took over an hour each way. Mission controllers had to plan every maneuver carefully in advance. They couldn't adjust on the fly. They couldn't respond to unexpected events in real time. The spacecraft had to operate largely autonomously, following pre-programmed instructions and making its own decisions when things didn't go as planned. Today, Voyager 1 is over 24 billion kilometers from Earth. It's been traveling since 1977, nearly 50 years now, and it's still sending back data. But communication is painfully slow. It takes over 22 hours for a signal to reach Voyager 1, and another 22 hours for any response to come back. That's nearly 2 days for a single round trip. Communication. If Voyager 1 encountered a problem and sent an alert, we wouldn't know about it for almost a day. If we sent instructions to address the problem, they wouldn't arrive for another day. By then, the situation could have changed completely. Voyager 1 has to handle most issues on its own. The speed of light gives us no other choice, and Voyager 1 is still in our cosmic backyard. After nearly 50 years of continuous travel at about 17 kilometers per second, it's only about 24 light hours away. It hasn't even traveled one full light day from Earth. In astronomical terms, it's barely left home. The nearest star, Proxima Centauri, is about 4.24 light years away. That's about 8,000 times farther than Voyager 1's current distance. Even traveling at Voyager's speed, which is impressive by spacecraft standards, it would take about 73,000 years to reach Proxima Centauri. And that's the nearest star. Most stars are much, much farther away. The Milky Way galaxy, our cosmic home, is about 100,000 light years across. To cross our own galaxy at the speed of light would take 100,000 years. The galaxy contains somewhere between 100 billion and 400 billion stars, spread across a disk so vast that even light needs 100 millennia to traverse it. Our sun sits about 26,000 light years from the galactic center. Light that left the center of the Milky Way 26,000 years ago is only now reaching Earth. When that light began its journey, humans were still hunter-gatherers. Agriculture hadn't been invented. Writing wouldn't exist for another 20,000 years. The entire span of human civilization, everything from the first farms to the first cities to the space age, has happened while that light was traveling toward us. The nearest large galaxy to our Milky Way is Andromeda. It's a beautiful spiral galaxy, slightly larger than ours, containing about 1 trillion stars. And it's about 2.5 million light years away. The light entering your eyes from Andromeda tonight started its journey 2.5 million years ago. Your distant ancestors, barely recognizable as human, were walking the African savanna. That light has been traveling ever since, crossing the vast gulf between galaxies, finally reaching Earth tonight. These distances are so vast that they define a fundamental limit on what we can know about the universe. No matter how powerful our telescopes become, no matter what technologies we develop, we can never see light that hasn't had time to reach us. We can never receive information that's still traveling through space. We can never observe events that have no connection to our past. And this brings us to a profound realization. The speed of light isn't just the speed at which light travels, it's the speed at which the universe communicates with itself. It's the speed at which events in one place can influence events in another place. It's the cosmic speed limit, not just for travel, but for causation itself. Nothing that happens at one place in the universe can affect another place faster than light can travel between them. If a star explodes 100 light years away, nothing can prevent the consequences of that explosion, the light, the radiation, the shockwave through space, from taking 100 years to reach us. No warning can arrive sooner. No signal can outrun the light. No effect of any kind can travel faster. This means that the universe is divided, for any observer, into regions that can have influenced them and regions that cannot have influenced them yet. Events within a certain distance can have affected you. Their light, their gravity, their effects have had time to reach you. But events beyond a certain distance cannot have affected you yet. They're too far away. The universe is too young. The light simply hasn't had time to arrive. The edge of the observable universe is the boundary between these regions. It separates the part of the universe that can have influenced us from the part that cannot have influenced us yet. Beyond that boundary, events have happened. Stars have formed and died. Galaxies have evolved and merged. Perhaps planets have formed, and perhaps life has arisen. Perhaps civilizations have risen and fallen, building great works and asking great questions, and ultimately passing from existence. But none of it has reached us. None of the light, none of the gravitational waves, none of the neutrinos, none of the signals of any kind have had time to travel the distance. The universe beyond our observable horizon is real. It almost certainly exists. Astronomers have no reason to think space suddenly ends at our cosmic horizon. The universe beyond is probably similar to the universe within, filled with galaxies and stars and all the cosmic structures we observe here. But it's as disconnected from us, for now, as if it existed in another dimension. We cannot see it. We cannot interact with it. We cannot even know what it contains. This is why the edge of the observable universe exists. Not because there's a wall or a barrier, not because the universe ends, but because light takes time to travel. The universe has only existed for a finite amount of time. And those two facts together create a horizon beyond which we cannot see. And as we'll discover in the next part, this edge is even stranger than it first appears. Because while the universe is 13.8 billion years old, the edge of the observable universe is not 13.8 billion light years away. It's much, much farther. The reason for this involves one of the most profound discoveries in the history of science. The universe itself is expanding. Space is stretching. And this changes everything about how we understand the cosmic horizon. Now that we understand why there must be an edge to what we can observe, let's explore what the observable universe actually is. And let's start with something that confuses almost everyone when they first hear it. Something that seems to contradict basic mathematics, but turns out to reveal one of the most profound truths about our cosmos. The universe is about 13.8 billion years old, but the observable universe is about 93 billion light years across. That's a diameter of 93 billion light years, a radius of about 46.5 billion light years in every direction from Earth. Wait, stop. If the universe is only 13.8 billion years old, and light can only travel at the speed of light, how can we possibly see things 46 billion light years away? Light traveling for 13.8 billion years should only cover 13.8 billion light years. That's what distance equals speed times time tells us. So, shouldn't the farthest things we can see be only 13.8 billion light years away? This is where things get wonderfully, beautifully strange. This is where the universe reveals that it's far more interesting than simple arithmetic would suggest. The answer to this apparent paradox is that the universe has been expanding, and not expanding into something. Space itself has been expanding. The very fabric of reality has been stretching, growing, becoming more of itself ever since the Big Bang. And this expansion changes everything about how we measure cosmic distances. Think of it this way. Imagine you have a balloon with dots drawn on its surface. Each dot represents a galaxy. Now start inflating the balloon. As you blow air into it, the surface stretches. The dots all move away from each other. But notice something crucial. The dots aren't moving across the balloon's surface. They're sitting still on the rubber. It's the rubber itself that's stretching, carrying the dots with it. This is roughly what's happening to space in our universe. Distant galaxies aren't flying away from us like rockets zooming through a void. They're not traveling through space at tremendous speeds. The galaxies are sitting relatively still in their local regions of space, but the space between us and them is growing. New space is being created between us and distant objects, pushing them farther away without them actually moving. This distinction is critical. Nothing is violating the speed of light. No galaxy is traveling through space faster than light. But space itself can expand at any rate it wants. There's no speed limit for the expansion of space because nothing is actually moving through space. Now here's the key insight that explains the 93 billion light-year diameter. When light left a distant galaxy billions of years ago and began its long journey toward us, that galaxy was much closer than it is now. The light has been traveling through space for billions of years, faithfully moving at 300,000 kilometers per second, never slowing down, never stopping. But during all that time, space itself has been stretching. The galaxy that emitted the light has been carried farther and farther away by the expansion. Think about it like this. Imagine you're swimming across a river. You jump in and start swimming toward the far bank. But the river is getting wider as you swim. The banks are moving apart. You're swimming at a constant speed, but the far bank is getting farther away. By the time you reach the far bank, you've swum a certain distance through the water, but the far bank is now much farther from where you started than it was when you jumped in. This is exactly what happens to light crossing the universe. Light from a distant galaxy starts traveling toward us. It travels at the speed of light, covering about 9.5 trillion kilometers per year. But while it's traveling, space is expanding. The galaxy is being carried away. By the time the light finally reaches us after billions of years of travel, the galaxy that emitted it has moved much farther away than the light traveled. The light might have traveled for 13 billion years, but the galaxy is now 30 or 40 billion light years away. The light covered 13 billion light years of distance, but the starting point moved during the journey. This is why the observable universe is about 93 billion light years across, even though the universe is only 13.8 billion years old. We can see objects that were relatively close when their light was emitted, but have since been carried much farther away by the expansion of space. Let me put some actual numbers to this to make it concrete. The cosmic microwave background radiation is the oldest light we can possibly see. It's the afterglow of the Big Bang itself, the first light that was ever able to travel freely through space. This light was released when the universe was about 380,000 years old, which sounds like a long time but is actually very early in cosmic history. The universe today is about 36,000 times older than it was when this light was released. This cosmic microwave background light has been traveling toward us for about 13.8 billion years, essentially the entire age of the universe. Here's the remarkable part. When that light was emitted, the matter that emitted it was only about 42 million light years away from what would eventually become our location. Not billions of light years, millions. The universe was much smaller then. Everything was much closer together. The entire observable universe was compressed into a much smaller volume. But during the 13.8 billion years that light has been traveling toward us, space has expanded enormously. The matter that emitted that cosmic microwave background radiation, the hot plasma that released those photons when it cooled enough to become transparent, is now about 46 billion light years away. It's been carried away from us by the expansion of space far faster than we could ever hope to reach it. This leads to a startling conclusion. There are objects in our observable universe that are currently receding from us faster than the speed of light. Not because they're traveling through space faster than light, they're not. But because the space between us and them is expanding so rapidly that the total rate of separation exceeds light speed. This sounds like it should violate Einstein's special relativity, but it doesn't. Special relativity says nothing can travel through space faster than light. It says nothing about space itself expanding. Objects can be carried away by the expansion of space faster than light without traveling through space at all. They're just sitting still in their local region while the cosmic fabric stretches. Let me give you an analogy that might help. Imagine you're an ant walking on a rubber band at 1 centimeter per second. You start at one end and try to walk to the other end, but someone is stretching the rubber band. If they stretch it slowly, adding maybe half a centimeter per second of new rubber, you can still reach the other end. You're gaining on it. But if they stretch it fast enough, adding more than 1 centimeter per second of new rubber band, you'll never reach the other end. You'll walk and walk forever, but the distance will grow faster than you can cover it. You're moving forward, but you're falling behind. For extremely distant galaxies, this is exactly what's happening. The space between us is expanding so fast that light itself can't keep up. These galaxies are forever beyond our reach. Light they emit today will never reach us. Not in a billion years, not in a trillion years, not ever. No matter how long we wait, no matter how far that light travels, new space will be added between us faster than the light can cross it. This expansion of space is what defines the edge of the observable universe. The edge is located where the expansion of space exactly equals the speed of light. At that distance, about 46.5 billion light years away, space is expanding at precisely the rate that light travels. Light from objects at that distance is running on a cosmic treadmill, moving forward but staying in place. Beyond that distance, space is expanding even faster. Light from those regions is actually falling behind, getting farther from us even as it travels toward us. This boundary is called the particle horizon. It marks the maximum distance from which any light, any particle, any signal of any kind could have reached us since the beginning of the universe. It's the true edge of the observable universe. Within this horizon is everything we can potentially observe. All the galaxies, or the stars, or the cosmic structures that could have sent us any information since the Big Bang. This is our observable universe, our cosmic neighborhood, our piece of reality, and this observable universe is enormous. The observable universe contains approximately 2 trillion galaxies. Let that number sink in. 2 trillion. That's 2,000 billion. That's 2 million galaxies, each one containing millions or billions or even trillions of stars. Our own Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. That's already an incomprehensible number. If you counted 1 star per second, it would take you between 3,000 and 12,000 years to count all the stars in just our galaxy. And the observable universe contains 2 trillion galaxies like ours. The total number of stars in the observable universe is estimated at around 200 billion trillion. Written out, that's 200 sextillion. That's a 2 followed by 23 zeros. 200,000 million stars. If you tried to count all those stars, counting 1 per second without ever stopping, without sleeping, without taking breaks, it would take you about 6 trillion years. The universe has only existed for about 14 billion years. You'd need to count for more than 400 times the current age of the universe just to count the stars. And most of those stars have planets. Data from the Kepler Space Telescope and other surveys has shown us that planets are common, not rare. Most stars have at least 1 planet orbiting them. Many have several. The total number of planets in the observable universe probably exceeds the number of stars. Perhaps 10 to the 24th power planets exist within our cosmic horizon. That's a number so large that it loses all practical meaning. Within the observable universe, matter is organized into structures at various scales, like a hierarchy of cosmic organization. Stars cluster into galaxies. Our Milky Way contains its hundreds of billions of stars spread across a disk about 100,000 light-years in diameter. The stars orbit the galactic center, held together by gravity and the mysterious influence of dark matter that permeates the galaxy. Galaxies cluster into galaxy groups. The Milky Way is part of the local group, a collection of about 50 galaxies gravitationally bound together. The local group includes the Andromeda Galaxy, which is larger than the Milky Way with about 1 trillion stars. It includes the Triangulum Galaxy, smaller but still substantial. And it includes numerous dwarf galaxies, small collections of a few billion stars or less that orbit the larger members. The local group spans about 10 million light-years. Galaxy groups cluster into galaxy clusters. The local group is a relatively small group, but is part of the larger Virgo supercluster, which contains about 100 galaxy clusters and groups spread across about 110 million light-years. The Virgo cluster itself, at the heart of this supercluster, contains somewhere between 1,000 and 2,000 galaxies. And superclusters are organized into even larger structures. In 2014, astronomers discovered that the Virgo supercluster is itself just a small part of an even larger structure called Laniakea, which means immeasurable heaven in Hawaiian. Laniakea contains about 100,000 galaxies, spread across 520 million light-years. But even Laniakea isn't the larger structure. The observable universe contains cosmic filaments, enormous threads of galaxies stretching across hundreds of millions or even billions of light-years. These filaments form a cosmic web, a vast network of matter with galaxies clustered along the threads and enormous voids between them. The Sloan Great Wall discovered in 2003, stretches about 1.37 billion light-years. It's a wall of galaxies, a relatively flat concentration of matter threading through space. The Hercules Corona Borealis Great Wall might be even larger, perhaps 10 billion light-years across, though its existence and exact size are still debated. These structures are so large that they challenge our understanding of how the universe could have evolved to create them. Between these filaments are the cosmic voids. These are regions of space with very few galaxies, vast empty zones that make up most of the universe's volume. The KBC void is about 2 billion light-years across. If you were at the center of this void and looked out in any direction, you'd have to look about 1 billion light-years before seeing significant numbers of galaxies. You'd be surrounded by an enormous bubble of nearly empty space. These voids make up about 80% of the volume of the observable universe. When we talk about 2 trillion galaxies, we're talking about objects clustered along filaments and walls, with vast empty spaces between them. Most of the observable universe, by volume, is almost completely empty. Now let's talk about something crucial. How do astronomers actually measure these enormous distances? Because you obviously can't stretch a ruler to a galaxy millions or billions of light years away. You need indirect methods. You need clever techniques that use physics to convert observations into distances. The most direct method is parallax. As Earth orbits the Sun, our perspective shifts. We move from one side of Earth's orbit to the other, a distance of about 300 million kilometers. This shift in position causes nearby stars to appear to move slightly against the background of more distant stars. It's the same principle you use when you hold up your thumb and alternate closing each eye. Your thumb appears to move against the background. The closer your thumb is to your face, the more it appears to move. By measuring how much it moves, you can calculate how far away it is. For nearby stars, astronomers measure this parallax shift very precisely. The Gaia spacecraft, launched in 2013, has measured parallax for nearly 2 billion stars in our galaxy. It can detect shifts so tiny that it can measure distances to stars thousands of light years away. But parallax has limits. Beyond a few thousand light years, the shift becomes too small to measure accurately, even with our best instruments. The stars are so far away that their apparent motion is unmeasurable. For more distant objects, astronomers use what are called standard candles. These are objects whose intrinsic brightness, their actual luminosity, is known. If you know how bright something actually is, and you measure how bright it appears to be, you can calculate how far away it must be for its light to have dimmed that much. Think of it like headlights on a highway at night. If you know how bright car headlights actually are, you can estimate how far away a car is by how bright or dim its headlights appear. A car whose headlights appear very dim is far away. One whose headlights appear bright is close. Cepheid variable stars are one type of standard candle. These are Lisa-Min stars that pulsate, swelling and shrinking on a regular schedule. They get brighter as they expand, and dimmer as they contract. And here's the crucial discovery made by astronomer Henrietta Leavitt in the early 1900s. The period of the pulsation, how long it takes to complete one cycle, is directly related to the star's actual brightness. A Cepheid with a short period, say 2 days, has a certain luminosity. A Cepheid with a longer period, say 30 days, is much brighter. By measuring the period of a Cepheid's pulsation, astronomers know exactly how bright it actually is. Then, they measure how bright it appears. The difference tells them the distance. Edwin Hubble used Cepheids to prove that the Andromeda Nebula was actually a separate galaxy, not just a cloud of gas within the Milky Way. By finding Cepheids in Andromeda and measuring their periods and apparent brightness, he showed that Andromeda was about 1 million light years away, far beyond the boundaries of our galaxy. This discovery, made in the 1920s, was revolutionary. It showed that the universe was far, far larger than anyone had imagined. For even more distant objects, astronomers used Type 1 as supernovae as standard candles. These are specific types of stellar explosions with a remarkable property. They all reach roughly the same peak brightness. A Type 1 supernova occurs when a white dwarf star, the dense remnant of a dead star, accumulates too much mass from a companion star. When the white dwarf's mass reaches a critical threshold, about 1.4 times the mass of our Sun, it can no longer support itself against gravity. It collapses and explodes in a thermonuclear detonation. Because this explosion always happens at the same critical mass, the physics is consistent. Every Type 1a supernova releases roughly the same amount of energy and reaches roughly the same peak brightness. This makes them excellent standard candles, and they're incredibly bright. A single type, a supernova, can briefly outshine its entire host galaxy. It can be visible from billions of light years away. By finding Type Ia supernovae in distant galaxies and measuring their apparent brightness, astronomers can calculate how far away those galaxies are. It was observations of Type 1a supernovae in the 1990s that led to one of the most surprising discoveries in the history of astronomy. The universe's expansion is not slowing down as everyone expected. It's speeding up. The expansion is accelerating, driven by something we call dark energy that we don't understand at all. The astronomers who made this discovery won the Nobel Prize in Physics in 2011. For the most distant objects, astronomers use redshift to estimate distances. As light travels through expanding space, its wavelength gets stretched along with the space. Light that started out with a short wavelength, like blue light, arrives with a longer wavelength, shifted toward the red end of the spectrum. Light that started out red arrives as infrared. Light that started out infrared arrives as microwave radiation. The amount of this stretching, called the redshift, tells you how much the universe has expanded since the light was emitted. And that tells you how long the light has been traveling, which tells you how far away the object was when it emitted the light and how far away it is now. Astronomers describe redshift with a number called Z. A redshift of Z equals 1 means the light's wavelength has doubled, indicating the universe has doubled in size since the light was emitted. A redshift of Z equals 10 means the wavelength is now 11 times longer than when it was emitted. The most distant galaxies ever observed have redshifts around Z equals 13. Their light has been traveling for over 13 billion years. When that light was emitted, those galaxies were only a few 100 million light years away. Now, after 13 billion years of cosmic expansion, they're over 30 billion light years away. These extremely distant galaxies are being studied by the James Webb Space Telescope, which launched in 2021. Webb can see infrared light, which is crucial because light from the earliest galaxies has been stretched so much by cosmic expansion that it's now in the infrared part of the spectrum. Webb is showing us galaxies that formed only a few 100 million years after the Big Bang, when the universe was young. But we can only see so far. There's an ultimate limit to how far back we can look with light. The cosmic microwave background is that limit. It's the oldest light in the universe, released about 380,000 years after the Big Bang, and it represents a wall in time, a moment before which we cannot see with electromagnetic radiation. Before about 380,000 years after the Big Bang, the universe was too hot for atoms to exist. Protons and electrons flew around freely, constantly colliding, never binding together. The universe was filled with a hot, dense plasma of charged particles. Light couldn't travel through this plasma. Every time a photon was emitted, it would almost immediately hit an electron and be absorbed or scattered. The universe was opaque. It was like trying to see through dense fog. Photons couldn't travel in straight lines. They couldn't carry information from one place to another. But as the universe expanded, it cooled. And about 380,000 years after the Big Bang, it cooled enough for electrons to bind with protons and form neutral hydrogen atoms. Suddenly, the universe became transparent. Photons could travel freely without constantly hitting charged particles. The light that was released at that moment, the photons that were finally free to travel, has been traveling ever since. It's been traveling for 13.8 billion years, gradually cooling as the universe expanded, its wavelength stretching from visible light to infrared to microwaves. Today, this ancient light fills the universe as a faint microwave glow, with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. This is the cosmic microwave background. It comes from every direction in the sky because that moment, that transition from opaque to transparent, happened everywhere in the universe, simultaneously. Look in any direction and you see cosmic microwave background radiation. It's the farthest thing we can see with light, the oldest photons in existence. The cosmic microwave background is remarkably uniform. In every direction, it has almost exactly the same temperature. This tells us something profound. The early universe was extraordinarily smooth. Matter was spread almost evenly throughout, with only tiny variations in density. But those tiny variations were crucial. They were only about 1 part in 100,000. If one region had a density of 100,000 particles, a neighboring region might have 100,001. That's almost perfectly uniform. But those slight differences had consequences. Regions that were slightly denser had slightly stronger gravity. Over hundreds of millions of years, that extra gravity pulled in more matter from surrounding regions. The dense regions got denser. The sparse regions got sparser. Eventually, the overdense regions collapsed under their own gravity to form the first stars, the first galaxies, the first clusters of galaxies. Every galaxy in the observable universe, including the Milky Way, every star, every planet, every atom in your body, traces its origin back to those tiny density fluctuations in the cosmic microwave background. You exist because one region of the early universe had slightly more matter than average. That slight excess evolved over 13.8 billion years into you. Scientists have mapped the cosmic microwave background in exquisite detail using satellites like COBE, WMAP, and Planck. These maps show the tiny temperature variations across the sky, representing those primordial density fluctuations. They're like a baby picture of the universe, showing what everything looked like when the cosmos was only 380,000 years old. Here's something profound to consider. When you observe the cosmic microwave background, you're not looking at a wall in space. You're looking at a wall in time. The cosmic microwave background comes from every direction because light from that era has had time to reach us from everywhere within our observable universe. Imagine the surface of a sphere centered on Earth with a radius of about 46 billion light years. That's the current distance to the matter that emitted the cosmic microwave background we observe today. That matter has been carried away from us by 13.8 billion years of cosmic expansion. This sphere is called the surface of last scattering. Everything within this sphere is part of our observable universe. Light from within this boundary has had time to reach us. Everything beyond this sphere has not yet had time to send us any light. It's beyond our cosmic horizon. This is the edge of the observable universe, not a physical barrier, not a wall you could touch, but a limit in time that translates to a limit in space. The maximum distance from which light could have reached us since the universe began. But can we see beyond the cosmic microwave background? Can we detect events from even earlier in the universe's history? Potentially yes. Not with light, but with other signals. Gravitational waves can pass through matter. They're ripples in space-time itself, and they don't interact with plasma or atoms the way light does. If the Big Bang or the era of cosmic inflation produced gravitational waves, those waves would have passed right through the opaque early universe. They might still be washing through the cosmos today, carrying information from the first instance after the Big Bang. Scientists are searching for these primordial gravitational waves. They're looking for subtle patterns in the cosmic microwave background that would indicate gravitational waves from the early universe. They're building incredibly sensitive detectors that might someday catch these ancient ripples directly. Neutrinos are another possibility. These ghostly particles barely interact with ordinary matter. They could have passed through the opaque plasma unimpeded, carrying information from before the cosmic microwave background was released. In principle, neutrinos from just 1 second after the Big Bang might still be detectable today. But detecting them is extraordinarily difficult. Neutrinos interact so weakly that trillions of them pass through your body every second without leaving any trace. Building detectors sensitive enough to catch ancient neutrinos from the early universe is a tremendous challenge that we haven't yet overcome. For now, the cosmic microwave background remains our deepest view into the past. It shows us the universe as it was 380,000 years after the Big Bang. Everything earlier is hidden behind a wall of hot plasma that no light could penetrate. But what we can see is remarkable enough. 2 trillion galaxies, 200 billion trillion stars, cosmic structures stretching billions of light years, all of it contained within a sphere 46.5 billion light years in radius. All of it visible to us because its light has had time to reach us across the vast gulf of cosmic expansion. This is the observable universe, our window onto reality, our piece of the cosmos. And at the edge of this window, where space is expanding at the speed of light, lies a horizon that separates what we can know from what we cannot. In the next part, we'll explore the true nature of this cosmic horizon. Why it's not really an edge at all. Why everyone has their own observable universe. And why the universe beyond our horizon is both real and forever unreachable. Now we come to the heart of this exploration. The strangest part of understanding the observable universe. Because the edge we've been discussing isn't like any edge you've ever encountered. It's not a wall, it's not a barrier, it's not a fence or a boundary or a line painted on the cosmic floor. It's not even really a thing at all. It's something far more subtle and far more strange. It's a horizon. To understand what this means, think about the horizon on Earth. When you stand on a beach and look out at the ocean, you see a line where the water appears to meet the sky. That's the horizon. Everything beyond that line is hidden from view. You can't see what's there. Ships sailing away from you seem to sink below that line, disappearing hull first, then mast, then vanishing entirely. But you know perfectly well that there's more ocean beyond that line. The horizon isn't the edge of the world. It's not where the water ends. It's simply the limit of how far you can see from where you're standing. If you get in a boat and sail toward the horizon, something interesting happens. You don't reach the horizon. You don't hit a wall or fall off an edge. The horizon moves with you. As you sail forward, new ocean appears ahead of you while the shore behind you eventually sinks below the horizon and disappears. The horizon is always the same distance away, always surrounding you, always marking the limit of your vision. The horizon isn't a place. It's not a location you can visit. It's a geometric consequence of standing on a curved surface with limited sight lines. Someone standing on a different beach has a different horizon. Someone on a ship in the middle of the ocean has their own horizon, centered on their location. Everyone has their own personal horizon, determined by where they're standing. The edge of the observable universe works the same way, but it's even stranger because it's a horizon in both space and time. It exists because of the finite speed of light combined with the finite age of the universe. And just like the horizon on Earth, it's personal. It's centered on the observer. It moves with you wherever you go. Let me explain this carefully because it's crucial to understanding what the cosmic edge really is. Imagine an alien civilization living on a planet in a galaxy near the edge of our observable universe. Let's say they're about 40 billion light years away from us in the direction of the constellation Ursa Major. From our perspective here on Earth, they're near the frontier of what we can see. Light from their location has been traveling for billions of years to reach us. They're at the very limit of our cosmic vision. You might think that from their perspective, they're also at the edge of something. They're near the boundary of the observable universe, so they must be able to see that boundary somehow. Perhaps they look out and see the edge of space, or a wall, or some kind of cosmic barrier. But that's not what they experience at all. From their perspective, they're not at any edge. They're at the center of their own observable universe. They can see the same distance in every direction that we can. Their observable universe is exactly the same size as ours. They're surrounded by galaxies and cosmic structures in every direction, with no edge visible anywhere. This seems contradictory. How can they be near the edge of our observable universe but at the center of their own? The answer is that the edge isn't a fixed location in space. It's defined by the observer. From Earth, we can see everything within a certain distance of our location. That's our observable universe. From that distant alien planet, they can see everything within the same distance of their location. That's their observable universe. The two spheres overlap but don't coincide. Part of their observable universe overlaps with ours. They can see some of the same galaxies we can see. The Milky Way, for instance, is within their observable universe. They can observe us, assuming they have telescopes powerful enough. We share some of the same cosmic neighborhood, but part of their observable universe extends into regions we cannot see. In the direction opposite to us, away from the Milky Way, they can see galaxies that are beyond our horizon. Those galaxies are visible to the aliens, but forever invisible to us. At the same time, we can see galaxies that are beyond their horizon. In the direction opposite to them, we can see galaxies that they will never be able to see. Those galaxies are within our observable universe, but beyond theirs. Every observer in the entire universe has their own observable universe, centered on themselves. Each one is the same size, but each one is centered on a different location. They overlap in complex ways, sharing some regions while having exclusive access to others. This means something profound. No observer anywhere in the universe is at any real edge. Everyone is at the center of their own cosmic vision. The edge surrounds every observer equidistantly, like the horizon surrounds everyone on Earth's surface. If you could somehow teleport 40 billion light years in any direction, you wouldn't find yourself at the edge of the observable universe. You'd just be in a different location with your own observable universe, centered on your new position. The edge would still be the same distance away in every direction. You'd have moved, but the edge would have moved with you. This is what makes the cosmic horizon so fundamentally different from any edge in everyday experience. It's not a universal boundary that everyone sees in the same place. It's a personal boundary determined by your location. There's no place in the universe where you could stand and touch the edge of the observable universe, because the edge isn't a place. It's a limit of perception based on where you are. Now let's think about what this means for the actual universe beyond our horizon. Almost certainly, space continues beyond the edge of our observable universe. There's no reason to think space suddenly stops at our cosmic horizon. The horizon is just where light has had time to reach us. Beyond it lies more space, more galaxies, more of the same cosmic structures we see within our observable universe. The observable universe is like a window onto a much larger reality. We can see through our window, but we can't see beyond its frame. That doesn't mean there's nothing beyond the frame. It just means we can't observe it from our current position. How much larger might the actual universe be? Current cosmological models suggest the universe might be vastly larger than the observable part. Some models, based on measurements of the universe's geometry and the patterns in the cosmic microwave background, predict the entire universe is at least 250 times larger in diameter than what we can observe. Other models suggest the universe might be infinite. Let me try to convey what an infinite universe would really mean, because it's one of the strangest ideas in all of cosmology. If the universe is infinite, it goes on forever. There's no edge anywhere, no boundary, no place where space ends and something else begins. Pick any direction and travel forever. You'll never reach the end because there is no end. Space just continues, filled with galaxies and stars and cosmic structures, forever and ever without limit. In an infinite universe with roughly uniform properties, something remarkable follows from pure mathematics. Everything that can happen does happen. Not just once, but infinitely many times. Think of it like shuffling a deck of cards. There are only a finite number of ways to arrange 52 cards. If you shuffled infinitely many times, eventually you'd produce every possible arrangement. You get the same arrangement many times, infinitely many times in fact, because infinite shuffles guarantee infinite repetitions of any possible outcome. The universe is like that deck of cards, but far more complicated. There are only a finite number of ways to arrange the atoms and particles in a given region of space. An enormous number of ways to be sure, but finite. If you have infinite space, you have infinitely many regions. And eventually, purely by chance, you get regions arranged identically. This leads to strange and unsettling conclusions. If the universe is truly infinite and roughly uniform on large scales, with the same laws of physics everywhere and similar distributions of matter, then somewhere out there is another galaxy virtually identical to the Milky Way. Somewhere is another solar system virtually identical to ours. Somewhere is another Earth with another you listening to these exact words right now. This isn't science fiction. It's not wild speculation. It's a straightforward mathematical consequence of infinity combined with random variation. In an infinite universe, any configuration that can exist does exist. Any arrangement that's possible actually occurs, and it occurs infinitely many times. How far away would your nearest identical copy be? Physicists have calculated this, and the answer is absurdly, incomprehensibly far. About 10 to the power of 10 to the power of 29 meters. That's a number so large that writing it out would fill more pages than atoms exist in the observable universe. It's so far beyond our observable horizon that it's meaningless in any practical sense. But in an infinite universe, meaningful or not, your copy exists. An infinite number of copies exist, each one living their life identically to yours, thinking they're unique, having no idea that infinitely many versions of them are scattered across an infinite cosmos. Now, we don't actually know if the universe is infinite. It might be finite but unbounded, like the surface of a sphere. On a sphere's surface, you can travel forever in any direction without hitting an edge. The surface has no boundary, but the total area is finite. You can walk around the entire surface if you walk long enough, eventually returning to your starting point. The universe might be like this in 3 dimensions. You could travel forever without hitting an edge, but the total volume would be finite. If you traveled far enough in one direction, you might eventually return to where you started, having circumnavigated the entire cosmos. Current observations don't definitively tell us which possibility is correct. The observable universe appears flat, or very nearly flat, which is consistent with either an infinite universe or a very large finite one. We may never know for certain which case applies. But whether the universe is infinite or merely vastly larger than what we can observe, one thing is clear. The observable universe is just a fraction of the whole. Our cosmic horizon is not the edge of existence. It's just the edge of our knowledge. This brings us to a deep and troubling question. What can we actually know about the universe beyond our horizon? The direct answer is stark: nothing. We can't see it. We can't receive any signals from it. No light, no gravitational waves, no neutrinos, no information of any kind has reached us from beyond the horizon. By the very definition of the horizon, nothing from beyond it has had time to affect us. The universe beyond our horizon is causally disconnected from us. Events happening there right now have no effect on us. Our events have no effect on them. We exist in the same universe, presumably, but we might as well be in parallel dimensions for all the interaction we can have. But we can make inferences. We can assume, based on the principle that Earth and our location are not special, that the universe beyond our horizon is similar to the universe within it. This assumption is called the cosmological principle, and it's one of the foundations of modern cosmology. The cosmological principle states that on large scales, the universe is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. Wherever you are in the universe, whatever direction you look, you see similar structures, similar densities, similar laws of physics operating in similar ways. The cosmic microwave background provides evidence for this principle. It's remarkably uniform in every direction. The temperature variations are only about 1 part in 100,000. This tells us that the early universe was extremely smooth and similar everywhere we can observe. And there's no reason to think it was suddenly different just beyond the horizon. Now we need to discuss something crucial about our cosmic future, because the edge of the observable universe is not static, it's changing, and the way it's changing has profound implications. In one sense, the observable universe is constantly growing. As time passes, light from more distant objects has time to reach us. Every second, our cosmic horizon expands outward by about 300,000 kilometers. Every year, light from one more light year of distance arrives at Earth. Our window onto the cosmos is always getting a little bit bigger. But there's a competing effect, and it's winning. The universe's expansion is accelerating. Space isn't just stretching, it's stretching faster and faster over time. This acceleration is driven by something we call dark energy, a mysterious component that makes up about 68% of all the energy in the universe. As dark energy accelerates the expansion of space, it carries distant galaxies away from us faster and faster. Galaxies that are already very far away are receding at tremendous speeds. Some are already receding faster than light, carried by the expansion of space rather than moving through space. This creates a cosmic event horizon, different from the particle horizon we've been discussing. The event horizon marks the boundary beyond which light emitted today will never reach us, no matter how long we wait. Objects beyond this distance are receding so fast that their light will never bridge the growing gap. The event horizon is currently about 16 billion light-years away, much closer than the particle horizon at 46 billion light-years. This means there are galaxies we can see right now whose present and future are forever hidden from us. We see their ancient light, but everything happening to them now is beyond our ability to ever observe. And the event horizon is shrinking. As expansion accelerates, more galaxies cross beyond it every moment. They remain visible for now, their old light still streaming toward us, but gradually that light will redshift and fade until they vanish from view entirely. Billions of years from now, if intelligent beings still exist in what was once the Milky Way region, they'll see a very different universe. Most of the galaxies currently visible will have faded beyond the cosmic horizon. The accelerating expansion will have carried them so far away that no trace of them remains detectable. The cosmic microwave background will have stretched to wavelengths far beyond anything detectable. Its temperature will have cooled to essentially nothing. The evidence that the universe began with a hot, dense Big Bang will have been erased. Future astronomers will look out at the cosmos and see something profoundly different from what we see today. They'll see only the merged remnant of our local cluster of galaxies, floating alone in an apparent void. They'll have no way to know that trillions of galaxies once populated the observable universe. They'll see no cosmic microwave background to tell them about the Big Bang. They'll measure no cosmic expansion because there will be no distant galaxies to observe receding. Based on their observations, those future scientists might reasonably conclude that the universe consists of a single galaxy floating alone in an infinite, eternal void. They'd be wrong, profoundly wrong, but they'd have absolutely no way to discover their error. All the evidence would be gone. We're living in a special time, a cosmological window that won't remain open forever. Right now, we can observe the cosmic microwave background. We can see distant galaxies. We can measure the expansion rate and determine that it's accelerating. we can piece together the history of the universe from its fiery beginning to the present day. That window is slowly closing. The evidence is slowly fading. Information is being lost forever, not destroyed but carried beyond any possible reach. There's something melancholy about this realization. All those distant galaxies, with their billions of stars and countless worlds, perhaps with their own civilizations and observers and dreamers, they're real. They exist. They'll continue to exist for billions of years, but they're slipping away from us second by second as expanding space carries them beyond our reach. We'll never communicate with them. We'll never visit them. We'll never even know what happens to them. They're forever beyond our horizon, existing but unreachable. The universe beyond the horizon is just as real as the universe within it. We just can't see it. And as time passes, more and more of reality is slipping beyond our ability to observe. This is the true nature of the cosmic edge. It's a limit of knowledge, not a limit of existence. It's a boundary of causality, not a boundary of space. Beyond it lies more universe, more galaxies, more stars, perhaps more life and more minds wandering about their own horizons. We're all in the same cosmos, made of the same matter, governed by the same physics, part of the same grand story. The edge of the observable universe separates us in terms of information, but not in terms of existence. We share a universe even with regions we can never observe. And that's perhaps the most profound thing about the cosmic horizon. It reminds us that reality is larger than what we can know. The universe exceeds our ability to observe it. There's always more beyond the edge, continuing forever, or at least far beyond our sight. Now that we understand the nature of this cosmic horizon, let's explore what it means for our future, for the deepest questions about the cosmos, and for our understanding of where we fit in a universe that extends far beyond anything we can ever see. First, let's address a question that might have been nagging at you. If space is expanding everywhere, if every part of space is stretching, why doesn't everything expand? Why don't atoms get bigger? Why don't planets drift away from their stars? Why don't galaxies fly apart into scattered stars? The answer lies in the balance between expansion and the forces that hold things together. On small scales, the forces binding matter together are vastly stronger than the expansion of space. Hydrogen atom is held together by the electromagnetic force between the proton and electron. This force is enormously stronger than the gentle stretching of space. The expansion might add a tiny, immeasurably small amount of distance between the proton and electron, but the electromagnetic force instantly pulls them back together. The atom doesn't notice the expansion at all. The same is true for larger structures. Earth is held together by gravity. The gravitational attraction between all the atoms in our planet far exceeds any expansive force. The solar system is bound by the sun's gravity. The planets orbit in stable paths because gravitational attraction dominates completely over cosmic expansion at these scales. Even galaxies, despite being hundreds of thousands of light years across, are held together by gravity. The Milky Way's stars orbit the galactic center, bound by the combined gravity of all the stars and the vast amount of dark matter that permeates the galaxy. Cosmic expansion has essentially no effect on structures this tightly bound. Think of it like trying to stretch a rubber band that's glued to a rigid frame. You can pull on the rubber band all you want, but the frame holds everything in place. Gravity and electromagnetic forces are like that frame. They hold structures rigid against the stretching of space, but on larger scales, between galaxy clusters where no significant binding forces operate, the expansion of space dominates. Galaxy clusters are separated by tens or hundreds of millions of light years. There's no gravitational bond strong enough to hold them together against cosmic expansion. So they drift apart, carried by the stretching of space. Our Milky Way galaxy is gravitationally bound to Andromeda and the other galaxies in the local group. This collection of about 50 galaxies is held together by mutual gravitational attraction. The expansion of space is not strong enough to overcome this bond. The local group will remain intact even as the universe expands around it. In fact, the Milky Way and Andromeda are actually approaching each other. Their mutual gravity is pulling them together despite the expansion of space. In about 4.5 billion years, they'll collide and merge, forming a single large elliptical galaxy. Some astronomers have nicknamed this future galaxy Milkomeda. So the long-term future of our cosmic neighborhood is isolation. The local group will merge into a single gravitationally bound structure, but everything beyond will drift away into the growing emptiness. Our descendants, if any exist in the deep future, will inhabit an island universe surrounded by void. Now, let me tell you about some of the most remarkable observations pushing our knowledge to the very edge of what can be seen. The James Webb Space Telescope, launched in 2021, has revolutionized our view of the distant universe. Its infrared vision allows it to see light that has been stretched by cosmic expansion from visible wavelengths into the infrared. This means it can observe galaxies from the earliest epochs of cosmic history. Webb has detected galaxies with redshifts above 13. The light we're seeing from these objects has been traveling for over 13 billion years. It was emitted when the universe was less than 400 million years old, just a few percent of its current age. When that light began its journey, those galaxies were less than 2 billion light years away from our location. But during 13 billion years of travel, space has expanded enormously. Those galaxies are now over 30 billion light years away. What's truly remarkable is that these early galaxies exist at all. The universe was so young when they formed. There hadn't been much time for gravity to pull matter together, for stars to form and gather into galaxies. Our theoretical models predicted that early galaxies should be small, dim, irregular blobs of stars just beginning to coalesce. But Webb has revealed something unexpected. Some of these ancient galaxies are surprisingly large and mature. They contain billions of stars. Some appear to have already formed organized structures like disks and bulges, features we thought took much longer to develop. A few seem to contain more stars than our models say should have been possible to form in the time available. These observations are forcing astronomers to reconsider how galaxies formed in the early universe. Either stars formed faster than we thought, or massive galaxies assembled more quickly than our models predicted, or something about our understanding of the early universe is incomplete. Webb is showing us that the cosmos still has surprises waiting at the edge of observation. Each new discovery pushes our knowledge closer to the ultimate limit. Not the edge of space, but the edge of time. We're seeing further and further back toward the moment when the first light emerged from the cosmic dark ages. Before those first galaxies, there was a period with no starlight at all. For perhaps 200 to 400 million years after the cosmic microwave background was released, the universe was filled with neutral hydrogen gas, slowly cooling and clumping under gravity, but producing no light. This era is called the Cosmic Dark Ages because the universe was literally dark. No stars had yet formed to illuminate it. We've never observed the Cosmic Dark Ages directly, but we have ways to potentially detect them. Neutral hydrogen emits a characteristic radio signal at a wavelength of 21 centimeters. By searching for this signal from the early universe, stretched by cosmic expansion to wavelengths of several meters, astronomers hope to map the Dark Ages and watch the first stars ignite. This is extraordinarily difficult. The signal is incredibly faint after traveling for over 13 billion years. It's overwhelmed by much stronger signals from our own galaxy and from human-made radio interference. But projects like the Hydrogen Epoch of Reionization Array and the Square Kilometer Array are attempting this observation. Success would reveal an era of cosmic history we've never seen, the transition from darkness to light. But there's an even more fundamental edge to our knowledge. The cosmic microwave background shows us the universe at 380,000 years old. Before that, the universe was opaque. What about the very beginning? What happened in the first moments after the Big Bang? And perhaps the deepest question of all, what came before? The first fraction of a second after the Big Bang was an era of almost inconceivable extremity. Temperatures were so high that particles and antiparticles were constantly created and destroyed in a seething quantum foam. The fundamental forces of nature, which today are distinct, were unified into a single superforce. Space itself may have been wildly different from what we experience now. During a period called cosmic inflation, thought to have occurred at about 10 to the minus 36 seconds after the Big Bang, space expanded exponentially fast. In a tiny fraction of a second, a region smaller than an atom expanded to become larger than the entire observable universe today. This inflation smoothed out any irregularities in space, explaining why the universe looks so uniform in every direction. It also generated the tiny density fluctuations that eventually became galaxies. We can't observe this era directly with light. The universe was opaque, and anyway, normal matter didn't exist yet in the form we know it. But we might be able to detect echoes of this primordial epoch through gravitational waves. Gravitational waves are ripples in space-time itself, predicted by Einstein and first directly detected in 2015. They pass through matter almost unimpeded. Unlike light, gravitational waves from the first instant of the universe would have traveled through the opaque early cosmos without being absorbed. If cosmic inflation happened, it should have produced a background of gravitational waves that still fills the universe today. These primordial ripples would be incredibly faint, but they might leave subtle signatures in the cosmic microwave background, patterns in the polarization of that ancient light that we could potentially detect. Scientists are searching for these signatures. The detection would be revolutionary. It would give us information from an era we can't access any other way, pushing our knowledge back to within a tiny fraction of a second of the Big Bang itself. It would be like hearing an echo from the moment of creation. And what about before the Big Bang? What triggered the initial expansion? What existed before time began? This is the ultimate question, and we genuinely don't know the answer. Several ideas have been proposed, each strange and fascinating in its own way. One possibility is that the Big Bang emerged from a quantum fluctuation in a pre-existing vacuum. In quantum physics, empty space isn't truly empty. It seethes with virtual particles popping in and out of existence. Some theories suggest that our entire universe could have emerged from such a fluctuation, a random event in a timeless quantum foam that happened to spawn a cosmos. Another idea is eternal inflation. In this model, inflation doesn't just happen once. It's the natural state of most of space. Inflation is constantly occurring, and occasionally regions stop inflating and become bubble universes like ours. If this is true, our universe is just one bubble in an infinite foam of universes, each with potentially different properties, constantly being created throughout an eternal inflating space. Some theories suggest our universe might be part of a cycle. The universe expands, eventually reaches a maximum size, then contracts back to a point before bouncing and expanding again. This cyclic cosmology would mean there was a previous universe before ours, and there will be another after. Time would extend infinitely into the past and future, with big bangs marking transitions between cycles rather than absolute beginnings. Other physicists have suggested that the question itself might be meaningless. If time began with a big bang, then asking what came before is like asking what's north of the North Pole. There's no answer because the question doesn't make sense. Time simply doesn't extend to before the beginning. We may never know which of these ideas, if any, is correct. The beginning of the universe, like the edge of the observable universe in space, may represent a fundamental limit to what we can ever discover. Some truths about the cosmos might be forever beyond our reach. This brings us to an interesting implication of the cosmic horizon for one of the great questions in science. Are we alone in the universe? The observable universe contains perhaps 200 billion trillion stars. If even a tiny fraction of them have planets, and if even a tiny fraction of those planets can support life, and if even a tiny fraction of life-bearing planets develop intelligence, there should be countless civilizations scattered across the cosmos. And yet, we've detected no sign of them. No radio signals, no laser communications, no evidence of massive engineering projects. The universe appears silent. This puzzle is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The cosmic horizon offers a sobering perspective on this question. Even if civilizations are common, most of them are beyond our horizon. We couldn't detect them even in principle. Their signals haven't had time to reach us. They might be thriving in galaxies we'll never see, completely unaware of our existence just as we're unaware of theirs. And even within our observable universe, the distances are immense. A civilization in a galaxy billions of light years away might have risen and fallen long before their light reached us. We'd be observing their past, seeing their galaxy as it was billions of years ago, with no way to know what became of them. The accelerating expansion makes this even more profound. Civilizations that might exist in distant galaxies are being carried beyond our event horizon. Even if they're broadcasting signals right now, those signals will never reach us. They're slipping away into the cosmic darkness, forever beyond contact. If intelligent life is rare, the cosmic horizon might ensure that civilizations never meet. Each one might arise, flourish, and perish in complete isolation, never knowing that others existed in the vast cosmos beyond their horizon. Or perhaps the horizon is the answer to the Fermi paradox itself. Perhaps the universe is teeming with life, but the distances and horizons ensure we'll never detect each other. We might be surrounded by company we can never contact. Now let's reflect on what all of this means for our understanding of knowledge itself. The edge of the observable universe reveals something profound. Reality is larger than what we can observe. The cosmos exceeds our ability to see it, measure it, comprehend it. No matter how powerful our telescopes become, no matter how long we wait, there will always be universe beyond our horizon. This is different from other limits in science. Usually limits are technological. We can imagine building better instruments to see farther, measure more precisely, detect fainter signals. Given enough time and resources, technological limits can be overcome. But the cosmic horizon is not a technological limit. It's a fundamental limit imposed by the nature of reality itself. Light travels at a finite speed. The universe has existed for a finite time. Those two facts create a barrier that no advancement can breach. And yet, look at what we've achieved despite this limit. We've measured the age of the universe to remarkable precision. We've determined its composition, the proportions of ordinary matter and dark energy. We've traced cosmic history from the first fraction of a second through the formation of atoms, stars, galaxies, planets, and eventually life. We've observed galaxies so distant that their light has been traveling since the universe was young. We've detected the cosmic microwave background, the afterglow of the Big Bang itself. We've discovered that the expansion of space is accelerating, revealing the existence of dark energy. We've constructed a coherent, testable, successful picture of cosmic evolution. A picture that makes predictions we can verify and that passes every test we devise. All of this from one small planet orbiting one ordinary star in one typical galaxy. All of this despite being confined to observing one finite bubble in a possibly infinite cosmos. The universe produced beings capable of understanding it. Matter arranged itself into patterns that can contemplate patterns. Atoms forged in ancient stars became brains that can conceive of atoms and stars. The cosmos evolved observers who can map the cosmos. We're the universe becoming aware of itself. And even though we're confined to one tiny region, our awareness extends the very limits of what can be observed. The edge of the observable universe is a limit, but our knowledge of that edge is a triumph. We've figured out where the boundary lies. We understand why it exists. We can describe what's beyond it, at least in general terms, even though we can never see it directly. So where does this leave us? The observable universe is finite. It contains everything that has had time to affect us since the beginning. Beyond it lies more universe, probably much more, possibly infinitely more. The edge is not a wall or boundary. It's a horizon defined by the speed of light and the age of the cosmos. Every observer has their own observable universe, and every observer is at the center of their own cosmic vision. The horizon is slowly growing as time passes, but the accelerating expansion means more of the universe is falling beyond our event horizon forever. The window onto the cosmos is closing, and beyond the edge, beyond everything we can see or ever hope to interact with, the universe continues. More space, more galaxies, more stars, perhaps more life, perhaps other civilizations looking out at their own horizons, seeing boundaries that don't coincide with ours, wondering about what lies beyond. We're all in the same universe, made of the same matter, governed by the same physics, part of the same cosmic story that began with the Big Bang and continues to unfold. The universe was here before us. It will continue after us. It extends beyond anything we can see, possibly forever. And we're here, looking out at the edge, knowing that there's more. There's always more. That's what the edge of the observable universe really tells us. Not that reality has a boundary, but that our vision does. And Beyond our vision lies more reality than we can ever see, more than we can ever know, more than we can ever reach. The edge isn't the end. It's just where our view stops. And the universe, vast and ancient and probably infinite, continues its story beyond the horizon, in realms we'll never witness. So the next time you look up at the night sky, remember what you've learned. Those stars you see are close neighbors. Behind them lie billions of galaxies. And beyond all of that, at the very limit of observation, lies a horizon that marks the boundary of everything light has had time to show us. But not the boundary of existence, not the edge of the cosmos, not the end of reality. The universe continues beyond that edge. It continues beyond our ability to observe it. It continues beyond our ability to comprehend it. And somehow, that's not diminishing. It's inspiring. Because it means there will always be more to wonder about. Always more to imagine. Always more mystery beyond the horizon. The edge of the observable universe is far away. But the wonder it inspires is here, inside each of us, every time we look up at the stars and realize they're just the beginning of what exists. Thank you for joining me on this journey to the edge of everything we can see. If you found this exploration meaningful, a like or subscribe would really help the channel continue making these deep dives into the cosmos. And remember, the next time you look up at the night sky, you're not just seeing stars. You're seeing across billions of years toward a horizon that marks the limit of light itself. But beyond that horizon, the universe continues. Vast, ancient, probably infinite, full of wonders we'll never see. And that's the most beautiful thing about the cosmos. It will always exceed us. It will always extend beyond the horizon. It will always have more. Good night. Sleep well under the stars. And know that those stars are just the nearest neighbors in a universe that has no end.